Okay, so for 4.6, when we look at the graphs of other trig functions, this one's going to be kind of short. I'm just going to go through about 2 examples with you. Of course, we've already looked extensively at sine and cosine and all the parts of the sine and cosine function. I'm going to do something very similar with tangent, but we're going to keep it a little more simplistic because, well, the tan graph is a little more simplistic. Let's look at the function y equals tan x. All right. So we're going to sketch our function over here. But to understand y equals tan x, we're going to go pretty much around our unit circle. And let's look at our quadrant angles. And kind of like we did before, -1, 0, 1, I'm sorry, 0, -1. And there's our theta. So we have pi over 2, pi, and 3 pi over 2. So what is tan? Well, we know that sine is the y value. We know that cosine is the x value. We also know that we have these reciprocal, or these what we call, not reciprocal, quotient identities. The quotient identities tell us, well, tan x equals sine x over cosine x. So that means tan x, when we relate that to the x and y values on a unit circle, we're looking at y over x. So that's important. You want to think of it as y over the x value. All right, well, let's go to 0. 0 degrees, y over x is just 1 over 0. It's just 0. So tan of 0 we know is 0. We have our theta along here. What happens when you go out to pi over 2, though? And this one's kind of important to think about. Tan of pi over 2 would actually end up being y over 0, which is undefined. Okay, same thing would happen to 3 pi over 2, but you can think about 3 pi over 2 as tan of negative pi over 2. Oh, undefined. And of course we can say that tan of 3 pi over 2 is undefined. Because in all these cases, to get our quotient, using our quotient identity, we're dividing sorry, by 0, and it ends up obviously being undefined. When you have a graph and a value is undefined, we have a couple things occur. Sometimes you have a hole at that graph, but for the most part, you have what we call an asymptote. So what does that mean? Well, at pi over 2, at negative pi over 2, and if we would like to take this, let me just take this a little further. Let me draw this out. And at 3 pi over 2, we will have vertical get them a little bit thicker. There we go. Vertical asymptotes. Our sine graph does not go past these values. All right, I'm going to erase what I did here so I have more space. All right. We have our vertical asymptotes. All right, so what we need to really do is figure out, well, what's happening between these vertical asymptotes. Well, we know sine is 0, 0. And if you were to take sine of pi over 4, well, that's kind of a common one that you've probably worked with. We worked with a lot. It was +1. And sine of negative pi over 4, because it ends up in the 4th quadrant, is going to be -1. So we're going to get really close, then we're going to make a turn, then we're going to come, we're going to get really close, and essentially, you can put your graph into Desmos, you can see it much better. That's our tan function. Okay, same idea over here. The difference being, of course, tan of pi, if you look at your unit circle, is going to be 0. Because it's 0 divided by -1, which is just 0. So it's an intercept at 0. And you get the same kind of graph going on here. So your tan graph essentially, just don't like that curve. I'm going to make it look a little bit better anyway. There we go. Looks like this. And again, I strongly encourage you to have Desmos open while you're going through these videos and popping things into Desmos so you can kind of see them for yourself. So this means, now obviously if you had an amplitude change, if it didn't make that curve at 1, if it was all the way up at 5, you know, it would look very similar. So here, I'll do it in a lighter color here. If I wanted y equals tan, not y equals, let's do 5 tan. Changing the amplitude does not change the intercepts or the asymptotes. It just changes the stretch. So that would be kind of really stretched out and you would barely see the curve. That's kind of how that would work. If we're 1/5, it would be super, you know, instead of 5x, if we're 1/5, it would just be super stretched out. So you can see what the amplitude does. It just changes the stretch of the graph, but it really does not impact intercepts and asymptotes, which are the kind of the two most important parts of your tan graph. So like with sine, we always started on an intercept, went to a max, intercept, min, intercept. With cosine, one cycle of our cosine graph kind of started at 1, went to an intercept, went to the 1, meaning the maximum, maximum, intercept, minimum, intercept, maximum. And if those graphs had a negative sign out front, it just flipped it. All right, so this is your graph of y equals tan x in black. Asymptotes in red, asymptotes aren't changing. Let's pick green for y equals negative tan x. Well, y equals negative tan x is simply, asymptotes don't change. You're just starting high and going down. Think of it this way. With negative tan x, you know, if your graph moves down from left to right. With positive tan x, your graph moves up from left to right in between your asymptotes. So they are general tan functions. How can we use this information to sketch any tan graph? I'm going to kind of show you a shortcut way. So here's what you need to know. If it's positive, starts low, ends high between asymptotes. Negative, starts high, ends low between asymptotes. So what's important? Well, those asymptotes are pretty important. And then right directly in the center of your asymptote, you have an intercept. So basically, if you can find your asymptotes, you can sketch a tan graph. So let's try one. Let me show you how we can use those asymptotes knowing. So here it is. What do we know from this? We know that y equals tan x as asymptotes between, the x value goes between negative pi over 2 and pi over 2. All right. It's defined between negative pi over 2 and pi over 2. And then once we get to negative pi over 2 or pi over 2, we have an asymptote. All right. If you utilize that information, well, it's easy to find those asymptotes because watch. Suppose I want to graph y equals tan of 2x minus pi over 3. Couple things I want you to notice. Number one, What do we want to notice before you start your graph? Oh, positive. That means my graph goes in that direction. All right, got to know that. Other thing you want you to notice. Amplitude is 1. All right, so we don't really need to, sorry, keep coughing. We don't really need to deal with the stretch. If my amplitude is greater than 1, then you kind of stretch it out a little bit. And if your amplitude's less than 1, then you kind of squish it a little bit. But since my amplitude's 1, I don't even need to think about that. I can just draw a standard curve. We need asymptotes. All right, easiest way to figure out your asymptotes. We know this has, the period has changed. Here's what we know. Oh, my period. The period, which you got to be careful because your period is still that b value, which is 2. That's going to help impact your period. Normally you would do 2 pi for sine and cosine. We did 2 pi over b. So, but here's what you need to remember. Your classic tan goes from negative pi over 2 to pi over 2. It only has a period of pi. You learned that in the first half of chapter 4. Not a period of 2 pi, only a period of pi. So the period is pi over 2. So that is between the beginning, I don't want to say beginning, but between the first asymptote and the second asymptote of our one cycle, there's only a distance of pi over 2. All right, so that's good. And you can still find a phase shift. You can find all of this the same exact way you did for your sine and cosine. And that is simply going to be pi over 3 divided by 2. Divided by 2 is times a half, so that's pi over 6. So it shifted pi over 6. All right. That being said, the easiest way to deal with it is to find those asymptotes. So the quickest way to find the asymptotes is to kind of utilize the idea that pi over 2, x is between negative pi over 2 and pi over 2. Well, that's just for tan x. I don't have tan x. I got tan of 2x minus pi over 3. So replace your x with 2x minus pi over 3, and this will work every time. 2x over pi over 3 between negative pi over 2 and pi over 2. I want to change this so it's just x. So what that will give me then is what are the actual x values for this particular graph. Okay, so we need to solve for x. That's essentially what we're doing. And sorry about that again. I had to step off for a second. So if I didn't pick up exactly where I was, I apologize. So all you're going to do is solve for x in this inequality. So you're going to add pi over 3 to both sides. Because you're going to add pi over 3 to the center, equate to the center expression, which then means to keep it balanced, you got to add pi over 3 to the other ones. Get your common denominator and get it over 6, which then will give you, if you put it over 6, 2 pi over 6 minus 3 pi over 6, which is negative pi over 6, is just basic subtraction of fractions. And of course, pi over 2 plus pi over 3, put it over common denominator 6, you get 3 pi over 6 plus 2 pi over 6, and that becomes 5 pi over 6. Divide everything by 2. Divide by 2, you multiply by a half, so it actually is negative pi over 12 x and 5 pi over 12. So here you go. These are where your asymptotes are for this new function. So that means you have y equaling 2x minus pi over 3. So here's the graph. Tan of 2x. I forgot the tan. Tan 2x minus pi over 3. Oh, I have an asymptote of negative pi over 12. And I have an asymptote of 5 pi over 12. Draw your asymptotes. The intercept is always going to be directly in between. So if you can't figure out what's directly in between, you simply need to take 5 pi over 12 minus you add them up. Sorry, 5 pi over 12 plus negative pi over 12 is going to give you 4 pi over 12 pi over 3 reduces to pi over 3 and divide by 2. Add them, divide by 2. You're basically taking the average between these two values on your graph. You're trying to find the middle value. Add them up, divide by 2. Pi over 3 divided by 2. Don't forget, division of 2 is multiplication of a half, so it's pi over 6. So at exactly pi over 6, you will have an intercept. And to double check yourself the distance, so again, to find intercepts, add where your asymptotes are, divide by 2. You need the middle value between. So add them up, divide by 2. To do a check, remember, period, we found to be pi over 2. Well, the period is the distance from 5 pi over 12 minus negative pi over 12. That's plus, so that's 6 pi over 12, which is pi over 2. And it's exactly what our period should be. So that kind of tells you you're in pretty good shape. There's no amplitude change, so it's a pretty basic function. And there's a sketch of your tan curve. It's going through pi over 6 with asymptotes. And if you're not sure, you can pop onto Desmos. There we go. There it is. I already have it on there. Let me move it so it's in the screen. I put the graph. You can make that bigger. Hold on a second. There it is. So you can see I put in 2x minus pi over 3. There's our pi over 6. Your asymptotes aren't going to show up, but you can kind of take a look. There's 5 pi over 12. That's clear. That's an asymptote. And there's your negative pi over 12. So your asymptotes are there. Okay. Let me go back. Let me fix this now. There we go. And that's essentially how you get your tan curve. I'm going to leave you to explore cotangent. Take a look, because it's something you really got to get used to playing with Desmos. So what you should do is sketch the cotan function to see where the basic cotan is. And then from there, once you have the sketch of the basic cotan function, you would apply the same rules to go ahead to get your intercepts, your new asymptotes, and your new intercept. All right. Yeah. So again, cotan, plug it in, see what it looks like. I'm not going to give you cotan on the test, so you know, but you should On your own, just explore cotan in Desmos so you know what the basic cotan function looks like. But I want to talk about the other two functions, the reciprocal of sine and cosine, because these two are kind of interesting. We're just going to do one of them because, so we will work with, let's work with cosecant. We know cosecant is the reciprocal of the sine function. So I want to take a look at the graph. It's going to have, you know, everything's going to be the same. The way you find your amplitude, the way you find your period, the way you find your phase shift is all exactly like the sine function. All right, exactly. None of that changes. But because we know that cosecant x is the reciprocal of the sine function, I want to use that identity to allow us to kind of explore the cosecant graph. So what do I mean by that? Well, first, let's go ahead and sketch a sine graph. So I'm going to do that in another color. I will do that in orange. So I just want a basic sine graph, right? It kind of goes like this. Right down. There we go. All right, we got a sine graph. No problem. We know a lot about that sine graph. Here, let me get my drawn a little bit further out. Okay, what do we know? We know that is at 2 pi. We know that's at pi. We know that is 0. We know that is pi over 2. And that is negative 3 pi over 2. Okay. Cosecant's a reciprocal. Well, what is sine of 0 is 0. What is the reciprocal of 0? Undefined. We know sine of pi is 0. Cosecant of pi is the reciprocal of 0. Undefined. So your cosecant and then secant would work the same way, looking at cosine, have asymptotes. Those I am going to put in red. Where do we have an asymptote? At 0. Anywhere your sine function has an intercept, cosecant has to have an asymptote. Just by definition. We've got asymptotes. All right? No issue there. Here, it's a 1, right? What's the reciprocal of 1? Just 1. What's the reciprocal? Just 1. What you end up with your cosecant graph are a whole bunch of these parabola-looking things in between the asymptotes. And this one would be up here. So here's what's going to happen when it comes to a sine graph, a cosine graph, and you're going to have to do them fully, of course. But when you are given a cosecant or a secant on the test, what I am looking for is, can you sketch it based off of the reciprocal function I give you? So if I give you a sketch of a function and I give you the equation of the function I want graphed and I give you the sketch of its reciprocal, can you provide a sketch and give me information on the graph? That's what I'm looking for. So for example, let me grab a graph. So here's what you will see on the test. You will be given a function like a cosecant or a secant function. In this problem, I'm giving you a cosecant function. And take a look at what else you're given. You are given the actual function I want you to graph. All right? And then you'll see a picture of a function. That picture is just to guide and help you. That is not the picture I want you to do anything with, but you can use it as a guide and you can sketch the function over top of it. So again, everything else is the same as sine and cosine. Amplitude is just 1. Period of cosecant and secant graphs are the same as sine as cosine. In other words, it's 2 pi, so this would be 2 pi over b, which is 2 pi over 2. So it, from one cycle, from start to finish, is going to have a distance of pi. There's going to be a phase shift of your c over b, so it's pi over 3 over 2, just like a sine and cosine graph. And that's going to be pi over 6. All right, divide by 2 times a half, pi over 6. So you have the information, and then you say to yourself, okay, I know cosecant is a reciprocal of sine, so it's shifting, and on a sine graph, I start with an intercept, and since it's positive, and cosecant's positive, the sine graph would be positive, I go from an intercept to a maximum, to an intercept, to a minimum, so on, to an intercept again. But on a reciprocal function, those intercepts become asymptotes. So it is still helpful to know all your functions. In other words, it is still helpful to say, well, wait a minute, pi, break that into 4 sections, pi over 4, that's your distance between key points. But your key points are clearly going to change because what was an intercept, because this is a reciprocal function, is now an asymptote. To help you as a guide, you can come over to the graph and say, oh, that's because that's an intercept, that's an asymptote. That's an asymptote. That's an asymptote. So that's what I mean by you can use it certainly as a guide. You know your graph's going to look like this. But can you answer questions? Can you tell me the equations of those asymptotes? So let's start there. And as I said, not all points will be labeled on this graph. So it's still kind of helpful to say, okay, pi over 6 is my starting point. There it is. Pi over 6. But I still need to take pi over 6 and add a quarter of my period, so a quarter pi to that. Well, if I take pi over 6 and add a quarter pi, what is that? 2 pi over 12 is 5 pi over 12. Okay, so my next key point is 5 pi over 12. Then I take 5 pi over 12 and add a quarter pi. So that's 3 pi over 12. That's 8 pi over 12. 8 pi over 12 reduces to 2 pi over 3. So pi over 6 is my first important point. Pi over 2 is my second. There's my third. 2 pi over 3 plus pi over 4 is going to give me, so you put each of them over 12. That's 8 pi over 12, 8, 9, 10, 11 pi over 12. And I need one more. That's key point. Remember, there's 5 key points. You break your period into 4 sections to get your 5 key points. 11 pi over 12 plus pi over 4 is going to give me 11 plus 3. 14 pi over 12, which reduces to 7 pi over 6. Great. So then I come up to my graph and I fill in what I don't have. I've got pi over 6. This works out perfectly. There's 5 pi over 12. That's a key point. Oh, my graph already has 2 pi over 3. And you will be given some of these key points, but you got to fill in the rest. That's going to be a key point, 11 pi over 12. Oh, and I already have 7 pi over 6. So there's my key point. So then I can answer questions. Where are the asymptotes? Asymptotes are at x equaling pi over 6, x equaling 2 pi over 3, x equaling 7 pi over 6. Done. Where are the intercepts? Because you're going to be asked, that's another key point, intercepts. Where are my well, not intercepts, sorry. That's not a key point. There are no intercepts. Sorry about that. That's what happens when I do this from not looking at notes. Minimums and maximums. Do I have any minimum values? Yes. I have a local minimum right here. That's considered a local minimum because between those two asymptotes, there are no other minimum points. So that is occurring at 5 pi over 12 comma 1. Amplitude didn't change, it was just 1. Do I have a maximum? Yes. This is considered a max. It is the local max. There's no other points near it that are higher than it within those asymptotes. And that, of course, is at 11 pi over 12 comma negative 1. So you do need to fill in maximum points, minimum points, asymptotes. Like I said, we can still talk about intercepts. There are none. The reciprocal function, that sine function that's in black there, does have intercepts. But what you want to recognize is that your cosecant graph does not. So if you're asked for an intercept, your answer is just going to be none. All right. So do practice your other functions. And like I said, on the test, to do a reciprocal function, a cosecant or a secant, I will give you the graph of its sine/cosine reciprocal to help guide you in getting all those points. Cotangent, not on the test. Explore it in Desmos so you can do some of the math labs and stuff like that. Till next time.